Hello, this is a key for some extra problems that I have created with forces at angles because I know that they're pretty tricky and I just want to make sure that everybody has a pretty good understanding of them going forward. So I'll just kind of lay into it right away here. So this first one, the deal is on all of these we're going to have a couple of angles that are along a set of axes, and then there's going to be like one angle that's not on the same set of axes as the other, and so we need to break it into components. That is the strategy here. And so for this first one, force 1 and force 2 are along the xy axis, but there's this other weird third force which is not along the axes. And so what we can do is we can break it down by taking this force here and breaking it down into components, all right, and creating a triangle here, and then this is a nice right angle. And what this gives us is as I said, a way of comparing this force to the other forces. We know that this 5 newtons is actually right here. It is the hypotenuse of this right triangle. And we want to find the other sides here. And so what you can do is you can take advantage of the trig functions that you have and figure out what the other sides are. So what we'll have here is we know that, for instance, for the side that's opposite of 55, we can use the sine function. So we know that sine of 55 is going to give us whatever that opposite side is over our hypotenuse, which is 5. And so we end up with 5 times the sine of 55 equal to x. All right, and then if you calculate that, you should get 4.1 as the side length there. All right. So that means on this side, we've got a length of 4.1 newtons. All right, in a similar way, we can find the top side by saying that the cosine of 55 is equal to y, our adjacent side there, over 5, which is our hypotenuse, and then we solve that for y, and we get 5 times the cosine of 55 equals y, which in this case is equal to 2.87. And we get that this side is 2.87 newtons. Now, basically, what has to happen here is everything has to cancel out, and we've got these two forces. One is going or these two components of this force. One is going to the left, the other component is going down because this force overall is going down and to the left. And so we know that the left part of this force 3 needs to cancel out with that F2, which is going right. And so this ends up being equivalent here, and we end up having force 2 equal to 2.87 newtons. And then the top force needs to cancel out with the part of F3 that's going down. All right, because these are directly opposing each other. One is going directly up, the other one is going directly down. And so this needs to equal 4.1 newtons, which is the vertical part of that force 3. All right, and so that's kind of what we end up with there. On this next one, I give you I give you one force and an angle, and we have to figure out the things from that. And so again, you realize that force 1 and force 2 hopefully are along these nice xy axis, but force 3 is not along the axes. So it needs to be broken down into components. I would break it down this way. All right, there's a right triangle there. And so we're going to try and find the vertical part of this and the horizontal part. If you look at this, you should notice left and right, the only things we have are F1 is going to the left, and then this horizontal component of F3 is going to the right. And so, essentially speaking, this part here that's going right has to cancel out with F1, because it's the only, like F2 is only going up and down, so it can't cancel out. And so this has to be 10 newtons here. And that's kind of the key to figuring out this problem, because this 10 newton force, or this 10 newton side of this force has to cancel out with F1. And then we have some information that we can work with to find the other sides. So if we want to find the horizontal part, we know that the tangent of 70 is going to give us opposite over adjacent, so 10 over whatever that side is there, so I'll call it x. If we solve this, we end up with x times tangent of 70 equals 10, and then we divide both sides by tan 70, and we get x equals 10 over tan 70. All right, which gives us a value of 3.64. So this side is 3.64 newtons. Now, there are a couple ways that you can find the hypotenuse. One way is that you can use the Pythagorean theorem. Another way that you can find the hypotenuse is by using another trig function. In this case, the best thing to use would probably be sine of 70 because we were more confident about that 10. Either way is fine. I'm going to go ahead and use the sine method because I think it's a little bit better. And so what we know here then is the sine of 70 is going to equal opposite over hypotenuse. So I'm going to say, in this case, the opposite side of the 70 again is 10. The hypotenuse we are trying to find, so I'll call that y. Similar sort of thing here. We then say y sine of 70 equals 10. So y equals 10 divided by sine of 70. And what you end up with there is that y equals 10.6. All right, and so this side of this force is 10.6 newtons. So I'm going to take this work and just kind of put it off to the side. Oops. Okay. Now, the only thing actually that we have to think of here is the equivalencies again, and so we have to think what's canceling out with what. Well, in this case, this F2 is canceling out directly with the vertical component of that F3, and so that 3.64 cancels out here with the upward we'd have to have 3.64 to cancel that out. All right, so we know that the upward force is 3.64, and F3, we've already found that actually it's that 10.6. It's the hypotenuse of that. So 10.6 newtons is what we've got there. All right, and actually I'll go and box my answers in the first one just because I think it's good practice to do that. Alrighty. So for problem number 3 here, we're looking for the degree measurement and for the value of F3. Again, you find the angle here that's kind of skewed off of the axes, and in this case, it's this F3. Alright, so we want to figure out some information about this. This is our right angle here. So, things we know. Well, this one is going straight off to the left and up if you're looking at those components. If you look at the rest of it, you should see that actually the horizontal component of this has to cancel out directly with F2, so it's 6 newtons on the horizontal component of this, and the vertical component going up and down actually has to cancel out directly with F1, so we know that this is 8 newtons because they're the only things going up and down. And so that gives us the sides of that. You can use the Pythagorean theorem on this one and try and figure out the size of F3. The Pythagorean theorem should give you 10 there. A squared plus B squared equals C squared. You should get 10 newtons for the hypotenuse there. And then all that's left is we have to find, which is equal to our force 3. All right, and then all that's left is we have to find this angle. We know that theta, if we want to find an angle, we have to use an inverse trig function. Because 8 and 6 were our most directly known sides, I think that using the opposite and the adjacent sides makes sense for this unknown angle, and so I'm going to use the tangent function. So we'll say theta equals the tangent inverse of 8 over 6. opposite over adjacent. Okay, and if you do that, you should get that theta equals 53.1 degrees for our unknown angle. Alrighty, on to this last one here. This one's a little bit funny because we have the same situation where two of the forces are along a set of axes that are perpendicular to one another, and then this other force is at a weird angle. But this time they're not oriented with the regular xy axis. So the force that we actually want to break down in this case is this force here. Alright, and we want to try and get this into the same set of components, and so what we'll do is we'll break this down into components. Some things we know this is 12 for force 3, and so we can use some trigonometry to find the other sides there. So what we'll do to find the side that's opposite of the 40 degree angle, we're going to use the sine. So we know that sine of 40 degrees equals this unknown side over 12, all right, and then this simplifies to x equals 12 sine 40, which if you calculate it, you should get 7.7 newtons. So this side is 7.7 newtons. And then to find the adjacent side, it's very similar, except we're going to use the cosine this time. So we know that cosine of 40 is going to equal y over 12, our adjacent side over our hypotenuse, and then we end up with y equal to 12 times the cosine of 40, which in this case equals 9.19 newtons, which you can just probably round to 9.2. All right, so we know then that this side here is 9.2 newtons. All right, and then if you look, that 9.2 Newton force is going up and to the left, and it cancels out directly with our F2. So our F2 is also 9.2 newtons. And then the part of this force that is going up and to the right is canceling out directly with F1, which is going down and to the left. All right, so what we get is this has to equal the same thing. It has to cancel out with that 7.7 Newton force. Okay, so that is that. Those are just some basic force problems. So I'll have a few of those like that on the test, but what becomes a little bit more difficult is when I give you a word problem like this. And so in this one, it says that we've got a block of cheese and it's being dragged across the floor by a mouse, which is holding a string. I said the normal force between the block and the floor is 24 newtons, and I want you to find all of the other forces. And so the first thing to do here is to make maybe a system schema, or I'm just going to jump right to the FBD, but if you want to make a system schema to help you out, that might be a good idea. So we have here a force, thinking about the different forces on it, we've got gravitational force Fg on the block by the Earth. All right, we've got a normal force going upward. This is Fn on the block, and it is by the floor. Then we've got a force that's kind of going off down to the bottom. This is a tension force, F tension on the block by the mouse. All right, and then friction is always happening parallel to the two surfaces that are rubbing together. So as this block tries to slide over here to the right, there's a friction force that's going to be going over here. So there's a friction force on the block by the floor again. Alrighty, and so these are our forces that we're dealing with. If you look in the problem, it's helpful to figure out that this angle here is actually the same 75-degree angle that you have kind of in the picture. It's an analogous angle. So that's 75 degrees there, which means that if we took this and broke the tension force into components this way, we end up with a 15-degree angle in there. So now we think about the things that we have. It's a 2 kilogram block, so we know that the gravitational force is equal to 20 newtons. All right, and then we're also given the normal force. In the problem, it tells us the normal force is equal to 24 newtons. Now, some of you get confused about this because you think, okay, shouldn't the gravitational force and the normal force be the same? That's true if they're the only things acting in the vertical direction, but there is a component of this tension force where that mouse is pulling the block down a little bit. All right, there's this little downward part of the tension force, and there's a rightward part of this tension force. And so we have to figure out what that is. If you do some trigonometry on this triangle, you should figure out that the tension force, the downward component of that tension force, oh, actually, you don't do the trigonometry at this point. What we see is there's 20 newtons going down and 24 newtons going up as shown. And that means if we have to balance things out, we need another 4 newtons going down. So we know that this tension force, this component of it here, and actually I'm going to move this kind of off to the side. The downward component of this is 4 newtons for our Ft. All right, on the block by the mouse. All right. So the downward component there is 4 newtons because there needs to be 24 total down to cancel out with the 24 up. All right, and then we have this triangle, and I'm just going to make everything a little bit bigger so that it's easier to write everything in here. So we can find the other side of this triangle now using some trigonometry. And so if you do that, you should find that this side is actually 14.9 newtons as well, using trigonometry. And if that's the case, then the friction force is also equal to 14.9 newtons. So as I was saying, this friction force here then has to equal the same as that horizontal component of the tension. So our friction is also 14.9 newtons. All right. The overall tension force then, if we want to find that, we've got 2 legs of that tension force, and so what we can do is we can say, using the Pythagorean theorem, it's the square root of 4 squared plus the 14.9 squared, or you could use some trigonometry on this. It doesn't particularly matter. And what you end up getting there is that your tension force equals 15.5 newtons. Okay, and that's just looking at the 2 components of the tension force that we have and figuring out what the hypotenuse would be. Moving on to this problem here, lots of people look at it and they get confused because they start trying to make the FBD right off of this. This is the picture, and so we're going to make an FBD, but it's going to be not related to this. Well, it's going to be related, but it's not going to be right here on these 2 arrows that already exist. A big thing to recognize here is that this is actually a right angle here, and we're going to use that to take advantage of what we do where sometimes we change the axes that we're talking about. And so what we've got this object. I'm going to make the FBD for it. Going downward, we have a gravitational force. So we've got this downward FG on the sign by the Earth. All right, and then some other forces that we have here. We have a tension force that's going up at an angle of 30 degrees. So this is Ft on the sign by rope 1. Oh, sorry, that's rope 2. Then we have another one that's at an angle of 60 degrees off the horizontal going the other way, and so we've got Ft on the sign by rope 2. Okay, and the information that we're given here is that the tension in rope 1 is equal to 160 degrees. So this equals 160 newtons. And so what we can do here is actually break this gravitational force into a couple components so that it's on the same set of axes as these two tension forces, which are at 90 degrees to one another. And so rather than using the traditional XY axes and then having to break both of the tension forces down, what we'll do is we'll take the gravitational force and put it so that it's on the same set of axes as the tension forces are. So that way we only have to change one force. And so it goes that way, all right, here, and then we've got this right angle. And then there's a bit of a tricky thing here. What I kind of like to do is I just kind of draw this gravitational force in here. And we've got this 60-degree angle. We've got the 60-degree angle in this picture here. And then based on this and the fact that we know that this is another right angle here, we know that this angle, this smaller angle here, is 30 degrees, and then we know that this is 60 degrees here. And so that lets us know that in this picture here that this is the 60-degree angle, and down here this is the 30-degree angle. All right. So now we've got a 30, 60, 90 triangle, and we can do some trigonometry to it just like we normally would. The side that we know that Ft, the tension in rope 1, is 160 newtons. Sorry, I just noticed that that's not a 1, so I should fix it. This is rope 1. It's 160 newtons. And so if you look at this picture, you have to try and kind of see this, but the thing that goes along with that 160 newtons is actually this side of the gravitational force. You get that this is also 160 newtons. And that gives us some information that we can use to find the other parts of this triangle. If you use trigonometry, you should be able to find that this side is 92.4 newtons, all right, and then the overall gravitational force is 185 newtons. And then the next thing that we have to realize is that this portion here, this portion that's going down and to the left of the gravitational force, is directly in opposition to the tension force that's going up and to the right from rope 2. And so we've got this 92.4 newtons going down and to the left, and that equals this section here. And so this tension force is also 92.4. All right, and then I said, all right, so let's find the tension in rope 2 and the mass of the sign. And so we got, for this problem, the force of tension in rope 2, we found it to be 92.4 newtons. All right, and then the mass, okay, we have the gravitational force of this sign is 185 newtons, and so the mass is going to be that divided by 10, so 18.5 kilograms, because the gravitational force is 10 times the mass. All right, and so those are the answers there to that one. This next problem is another sort of ramp problem. So these should be hopefully pretty familiar to you by now. So we got to think of all the forces acting on this block. I'm going to draw hopefully here like a pretty large FBD. So the first thing is we've got gravity going down. So that's Fg on the block by the Earth. And then here I say that it's being pulled up a ramp. All right. So there's a tension force that's going at 20 degrees up the ramp. All right, and so this is Ft on the box by whatever that rope is. Okay. Careful here, actually, because there are two R's. There's going to be the rope and the ramp. So I'm going to call this on the box by the rope. All right, and then we have a normal force that's going to be occurring between these, and it's got to be perpendicular to the surface of the ramp. All right, so in this case, it's going to be going up here at this angle. All right, and that's going to be the normal force Fn on the box by the ramp. So in this one, these two forces are at a 90-degree angle to one another because one is going parallel to the ramp, up the ramp, and one of them is going perpendicular to the ramp, and so they should be perpendicular to one another. And so this is another case where we're going to take this gravitational force and break it down into components to try and get it along this other weird set of axes that the other two are on. You got to think about what angle this is going to be at, and so this is kind of how I start thinking about it. We've got gravity, which is going down. Okay, so we've got this, and then I'm going to draw this. This is the traditional XY plane. Then we've got this force that's going up at 20 degrees, this ramp that's going up at 20, and I'm just going to continue this line down here. So if this is 20 degrees here, then this is 20 degrees here, right? And then the angle between the gravitational force, which is straight down, and the opposite side of here of this ramp, this is going to be, that would be 70 degrees. And so you should hopefully see, oh no, yeah, 70 degrees. So you should see that this is 70, all right, and that it is analogous to this angle here, which is also 70 degrees. And that will help you do the math and the trig for figuring out the other parts of this force. And so that's kind of how I think about things in terms of the angles. And so now what we have to do is figure out the things that we don't know. We know that this is a 3 kilogram block, so that means that this is 30 newtons. You can then go through and do the trig on this one and figure out that this side is equal to 28.2 newtons, and that this other side is equal to 10.3 newtons. All right, and then looking at what these components of this gravitational force oppose, there's this one that's going down and to the left, and this other one that's going down and to the right. All right, the down and to the left component, the 10.3, is opposing the tension, so that means the tension force is 10.3 newtons. And the normal force is also, we can find this here, it is going up and to the left, and it's directly opposing that part of the gravity that's going down and to the right. All right, and so this actually ends up equaling the 28.2 newtons. Hopefully that's not too terribly difficult, but if you're still struggling with these problems, always feel free to come in and ask.